next topic is finite Fourier cosine and sine transform and their inversion formulas. So we have studied until now the cosine and sine transforms in the real intervals, which are defined in the real half interval. So say from 0 to infinity, these are the functions that are defined. So what is the need for studying this finite version of such transforms? In many applications, we are to deal with problems which are defined on finite intervals. So what we do instead is we create new formulas which would be valid for this finite intervals. So that is known as the finite version of the finite Fourier cosine and sine transforms, which are obtained from their corresponding counterparts, the Fourier cosine and sine series. So the next thing is we'll first study the finite Fourier cosine transform. So what is this? So for that, firstly we consider that the given function is f of t, which is piecewise continuous on this interval 0 to pi. So now here the interval here is the finite interval and it is defined for finite value 0 to pi. So then this is the notation FCN. It represents the operator here is this one. So that means we are saying Cn of the given function f of t. So Cn is the operator. So C represents cosine, N represents for finite, and Ft is the given function. So whatever is the result, we denote that by Fcn. So this is the result that we have, and its value, it is calculated through solving this particular integral. What is this? It is integration from 0 to pi f of t cos nt dt, where n is some discrete numbers. So this is the definition for finite Fourier cosine transform. To calculate its inverse, what we do, we just write the Fourier cosine half range series. What is that? It is given by f of t is equal to 1 by pi integration from 0 to pi f of t dt plus 2 by pi summation n varies from 1 to infinity integration 0 to pi f of t cos nt dt cos nt. So now if you compare this expression with the one we have just derived, so the integration from 0 to pi f of t cos nt, that is equivalent to this quantity Fcn, and if you see, this is same as this quantity, this particular quantity. So we have identified this to be the same as Fcn. Moreover, this first term here, if you substitute 0 in place of t, in place of f of t, right? So Fc of 0, what would be that? In place of omega, in place of n, right, we have Fcn defined to be like this. So if you substitute n is equal to 0 into this expression, you would have integration from 0 to pi f of t as such cos of 0t dt, and cos 0 we know it is equal to 1. So this expression is equal to 1 by pi integration from 0 to pi f of t dt. So this is the expression, and this is identified by this term Fc of 0. So we can write f of t as 1 by pi Fc0 plus 2 times this whole value including 1 by pi. So that is Fcn, right? So summation n varies from 1 to infinity Fcn cos nt. This is the expression for inverse finite Fourier cosine transform. So what we have done, we have shifted from f of t to Fcn when we applied this finite Fourier cosine transform. But for reversing it, we have to move from here to here. So that means we will input these quantities and we will have output of this quantity. So this inverse operation, that is defined through this series of this kind. That means you obtain the expression for f of t through these using this expression. So here you have Fcn inputted into the series and Fc calculated at the point 0. So this is the inverse finite Fourier cosine transform. Next is the finite Fourier sine transform. That is calculated in a similar way. The condition on f of t is that it should be piecewise continuous on this interval 0 to pi, and this finite Fourier transform of function f of t, that is given by this particular integral, that means integration from 0 to pi, because our interval here is finite interval. This is given to be finite interval, and it is the given function multiplied by the sine nt dt. And the notation for this is that this is the operator representing this finite form of Fourier sine transform. So what is this Sn? This S represents the corresponding sine transform. This N represents the finite form of this sine transform, and f of t is the given function. Whatever is the answer, that is given by f s of n. So this is the product that you obtain after the application of finite Fourier transform on the given function. For calculating inverse, we wanted to move from this function to again back to the function f of t. So for that we again need the Fourier sine half range series. In this case, Fourier sine half range series. Why this is required? You will see that in a moment, because we are taking the sine term here, so that means we'll also take the Fourier half range sine series in this term. So it is given by f of t is equal to 2 by pi summation n varies from 1 to infinity, integration from 0 to infinity, f of t sine nt sine nt. So now when you compare this expression with this one, you will see the value of this term, it is nothing but fs of n. So our series finally becomes ft, that is equal to 2 by pi summation n varies from 1 to infinity fsn sine nt. This is the inverse finite Fourier sine transform that you obtain. Next, let us see an example. We are given this function f of t, which is defined as 0 in this interval from 0 to pi by 2, and from the interval pi by 2 to pi it is defined to be 1. We are interested to calculate the finite Fourier sine transform of this given function. So let us see the finite Fourier sine transform. Its formula is given by integration from 0 to pi f of t sine nt dt. So we'll first break our interval from 0 to pi by 2 and then pi by 2 to pi, because our function is defined in this manner only. So in this interval 0 to pi by 2, the value of function is given to be 0. So it becomes 0 in this interval, and in the interval pi by 2 to pi, the function's value is given to be 1. So we have just substituted the function's value. Now we will perform this integration and this integration. So when you perform this integration, sine t, it would be cos nt divided by n, and limits varies from 0 to pi by 2. This is the integration, and when you substitute the limits, you will have it as 0. And then here again you will substitute, you will perform the integration, and the value that you will have here is actually you won't perform any integration here. Why? Because a function is multiplied by 0, so everything here would eventually be 0. So next you will only perform the integration here of this function sine nt, because it is being multiplied by 1. So its integration is minus cos nt divided by n, and the limits varies from pi by 2 to pi. That is the limits. So when you substitute this limit, t is equal to pi here and t is equal to pi by 2 here, so you have this expression. So you know what is the value of cos n pi? Cos n pi, that is equal to minus 1 raised to power n. Why? Because if you say cos of 1 pi, that is equal to minus 1. If you see cos of 2 pi, that is equal to plus 1. Cos of 3 pi, that is equal to minus 1. Cos of 4 pi, that is equal to plus 1. So we write all these combined by this expression. And what is the value of cos n pi by 2? For here we have different cases. When n is odd, its value is 0. When it is a multiple of 4 and it is an even quantity, obviously it would be an even if it is a multiple of 4. So in that case its value is equal to 1, and whenever it is not a multiple of 4 but it is an even quantity, so in that case its value is equal to minus 1. So this is the representation of the function that we obtained after applying finite Fourier sine transformation on the given function. So I think it is clear to you all. So if you have any